We're going to continue looking at volume of a solid revolution by disk and get into how something goes from being a disk to a washer. So this example asks to find the volume of the region bounded by f of x equals 4 minus x squared and g of x equals 3 that is revolved around y equals 3. So unlike the previous examples where we were revolving around the x-axis, we're now revolving around y equals 3, which is still a horizontal line, but it is not on the x-axis. So one thing you'll notice in the example is that we are not given any x values. So in order to determine the region, we have to set the functions equal to each other, as you can see right here, and solve for x. So it's a quadratic equation. Easiest way to solve this one is subtract the 4, divide by a -1, square root both sides to find out that our functions intersect at +1 and -1. You can then sketch a graph of this region, as you can see over here. And we've got a parabola above the horizontal line y equals 3, intersecting at x equals -1 and +1. And we're going to revolve around that line y equals 3. It's still a disk. Now, why is it still a disk? Because the region is right up against what we're revolving around. So there's no gap in between the region and what we're revolving around. You're going to find out in a little bit that we're going to do the same problem, but we're going to revolve it around the x-axis. So if we were to revolve this around the x-axis, then we would take this region and revolve it all the way around, which would leave this big gap in between and create a washer. Very much like a washer that you would use if you were, building something and you had to use, nuts and bolts and washers. So the washers, of course, are thin cylinders with the middle missing. Well, this is not one of those examples because we're revolving around y equals 3 up here, so there is no gap. So how do we do it? Very much the same way that we do it when we revolve around the x-axis. So it's still based on the geometric formula pi r squared times height. So we take our integral here from -1 to 1, pi, and then where does this radius come from? Well, earlier in this unit we talked about finding the area between two curves. So if you want to find this region, you take the top curve minus the bottom curve, as you can see right here. So the top curve, f of x, minus the bottom curve, 3, gives us the result 1 minus x squared. So keep in mind that f of x was 4 minus x squared, so it's really 4 minus x squared minus 3. 4 minus 3 is 1, so that's where the 1 minus x squared comes from. 1 minus x squared becomes our radius. So our integral is pi times the integral from -1 to 1 of our radius squared dx. This one also has symmetry, so what you'll see is when I rewrite my integral, I go from 0 to 1 instead of going from -1 to 1 because both sides of my region are symmetric, so they'll give me the same volume, so I just do half and double it. So it's 2 pi times the integral from 0 to 1 of our radius squared. Had to FOIL out my radius squared. It's nice that it's polynomial, so the integral of x to the 4th is x to the 5th times 1/5. The integral of -2x squared is x to the 3rd times 1/3, but that -2 out front makes it -2/3 x to the 3rd, and the integral of 1 is x. I then evaluate doing my upper limit minus my lower limit. It's nice that we have some zeros in there. And then a little bit of simplifying with the fractions. Get a common denominator of 15, simplify. 8/15 times 2 pi gives us 16 pi over 15. Could do this in the graphing calculator as well, but you would get an approximation. I don't have that in the notes, but it would be easy to calculate. Now, the next example says, let's do the same thing as above, but as I mentioned a little earlier, let's revolve it around the x-axis. So if I go back up to the picture, we're going to take the same region, but instead of revolving it right around y equals 3, we're going to take this region and revolve it all the way around the x-axis. So there's this big gap in the middle. Well, how do you account for the gap? becomes a washer. So what we have to do is take the volume of the outer region minus the volume of the inner region. There's a couple ways you could do this. You could set up two integrals. So you could do 2 pi times the integral from 0 to 1, because we still have that symmetry, of the outer function, which is 4 minus x squared, all squared dx. So that would be like if I had said, let's just take this upper curve back to the x-axis and revolve it, and there was no middle part missing. So we would have this big, almost like pill-looking shape. But we do have a gap, so we have to subtract off the volume of this inner part. So we subtract off the integral 2 pi times the integral from 0 to 1 of our inner function squared dx. I don't have the work for it here because I didn't work it out in my notes, but you'd be able to FOIL this out, integrate, evaluate. This would be the integral of 9, so that's an easy one. That would just become 9x, and then you would integrate it, and you would end up getting 136 pi over 15. It makes sense that the washer has a much bigger volume than the disk. If we go back up here, the disk is just revolving around this, so it's a very small solid. But when we revolve this around the x-axis, it goes all the way around and creates a much bigger solid. So when you see the answers, 136 pi over 15 compared to 16 pi over 15, because we're revolving the region around the x-axis, it creates a bigger solid. Another example of this would be to find the volume of the region bounded by f of x equals x squared, g of x equals negative x squared plus 2, and the y-axis, and revolve that around the x-axis. So this time we have x squared, our bottom curve, negative x squared plus 2, our top curve. They intersect here at x equals 1, which you would have to set them equal and figure that out unless you had a graphing calculator. And then the y-axis is also a boundary. If we're going to revolve this around the x-axis, there's this gap right here, this white space between our bottom curve and the x-axis, so it creates a washer. So you can see I wrote some notes here. The base does not rest on the axis of revolution, so the solid will have a hole in it, or really more like a gap. Rather than a disk, this forms a washer. Not really sure why I used exclamation marks, but I guess I got excited. So to do this, similar to the example that we just talked through above, you have an outer function, which I like to call big R, and an inner function, which I call R. How do you know which one is which? The outer function is farther away from the axis you're revolving around than the inner function is. And just like we mentioned above, to find the volume of a washer, you take the volume of the outer function first, minus the volume of the inner function. So our outer function will be the integral from 0 to 1 of negative x squared plus 2 squared, and don't forget your pi out front. So it's pi r squared dx. Our inner function is going to be x squared from 0 to 1 squared dx, and don't forget your pi. So it's pi times the integral from 0 to 1 of our inner function squared dx. Then once we have the volume of the outer, we subtract off the volume of the inner, and we get our answer. We can generalize this to get the volume formula for washers. So the thing that the volume formula for washers has in common with disks is that you're ultimately just taking the outer disk and subtracting off the inner disk. And when I say the outer disk, I mean the volume of the outer disk minus the volume of the inner disk. What's nice is you can write it as one big integral once you get the hang of it. Now, truth be told, some students like to write two separate integrals, one for the outer function and one for the inner function, which is totally fine. But many times, by writing it as the outer function squared minus the inner function squared in the same integral, you can simplify this before you integrate, and it saves a little bit of time. But ultimately, it's the same formula as disks, that geometric formula of pi r squared times height. The only difference is you have to take that outer radius squared minus the inner radius squared. One of the common mistakes with washers is that students will simply do the outer radius minus the inner radius, and they'll do that whole thing squared. But you have to square each of your functions separately, because ultimately you are doing one volume minus another volume. The work down here is the work that continues from the work above. So if you look up here, this was the problem we were looking at. This kind of shows the setup, and then the actual integration is down here. So you can see it's a pretty simple integration because we're dealing with polynomials. It's nice that we have 0 for our lower limit, and with a little bit of fraction work here, you get to your answer 8 pi over 3. Here's another example. Find the volume of the region bounded by the function square root of x and the function x squared that is revolved around y equals 4. This one's kind of unique because this time our region is down here. So the square root of x is actually what appears to be above, and x squared is below. And you could get that by plugging in values in between 0 and 1. For example, 1/2. The square root of 1/2 is actually going to be above 1/2 squared. Now, what's unique about this example is that we're now revolving around y equals 4, which is up here. So we're taking this region and we're revolving it all the way up and over. The process is the same, but here's the deal. Our outer region is actually what we would normally call the lower or bottom function. What do I mean by that? Well, if we take a look here, this is farther away from the axis we're revolving around, in this case y equals 4, than this. So our outer function is actually x squared, even though it's below. Our inner function is the square root of x because it's closer to the axis we're revolving around. So when we set up our washer integral, our outer function is 4 minus x squared. Now you might say, why is it 4 minus x squared? If you look at this blue line that I drew here, back to the outer function, I need to find that distance. So the distance from y equals 4 back to the x-axis is 4, and if I subtract off x squared, it gives me the resulting blue line. That's where the 4 minus x squared comes from. Similarly, my inner function is 4 minus the square root of x, because if I go from 4 back to the x-axis, that's obviously 4, and if I subtract off x squared, it gives me this resulting radius. So I would set up two integrals, or I could do it all as one, but ultimately I need pi times the integral from 0 to 1 of my outer radius squared dx minus pi times the integral from 0 to 1 of my inner radius squared dx. This is about as complicated as washer problems get. But then I would just, first I would have to simplify by foiling out each of my radius, and then I would integrate, evaluate. Again, it's nice that there's some zeros in there. Got some fraction work to do for sure. And ultimately you'd get to 71 pi over 30. On the AP test, on the Unit 8 test, numbers would not be quite as complex as these if you weren't allowed to use your calculator. However, could be on the calculator section, and that wouldn't be too bad anyway, because way back here you could have typed those integrals into your calculator and gotten the decimal approximation for 71 pi over 30.